is we are having the forces acting. So along this rope, of course, we have the tension, and then we can use a reference point. All right. Mostly we can use the center of gravity to be the reference point, but we can use this point. It's okay. And then at this point, we know the weight of this will be acting downwards. That's our mg. And then we have the normal reaction force to this direction. So that's normal reaction force. So that way this can be so short. And then because we are putting it in this direction, that is to the left, so we're gonna have friction force acting in this direction. So that should form the free force body diagram. Now the second question is about assuming that the truck pulls the container at a constant speed. That's very important, constant speed. Write an equation for the magnitude T of the string tension in the cable, right? So let's see how we do that. So we have the free force body diagram already now. So we have the force down, which happens to be the mg. We have the force up, which happens to be the normal reaction force. We have the friction force backwards, and then we have, of course, it's moving in this direction. However, the tension is pulling at an angle here, angle theta, and then this is our tension force T. So how to proceed from here, and we want to form an equation that will give us T. You can just make equations to balance the forces by applying Newton's laws of motion, like this. We know it's already moving toward this direction, so there is a movement. In other words, generally, the whole system is moving in this direction. So we know they're going to be Newton's second law of motion in the x direction. So that is in the x direction. And in the y direction, we know there's no motion at all, no movement. And therefore, that means for this situation, we can start with the forces on the vertical. The forces on the vertical, because we don't have any motion, we can say according to Newton's first law of motion, when we look at the y, or that is the vertical, how many forces do we have going in the up direction? We have one is a normal reaction force, that's one, and we have a component of tension, because this tension force has two components. Part of it is on the vertical and part of it is on the horizontal. So on the y upward direction, so we're going to say n, we have n, and then you add a component of the tension. So component of tension, which is vertical, is simply that is T cosine of theta, and then the upward forces should be equal to the downward forces, and the only downward force we have here is the mg. So we're going to have is equal to mg. That gives us equation 1. So, and that we've been able to apply the Newton's first law of motion. Now, because we have motion along the x-axis, meaning the system is moving to the left, then we can say Newton's second law of motion along the x-axis. However, as we shall see later as we deal with Newton's second law of motion, since the system is moving at a constant speed, just remember, if we say it's moving at constant speed, very good, no acceleration. So that would mean the acceleration is equal to 0, no acceleration. It therefore means our formula for F is equal to ma. That illustrates the Newton's second law of motion along the x-axis. And this is the net force. So it means therefore the net force also here will be equal to 0, because there's no acceleration. And therefore what will happen? Therefore we can now again add the forces. We can say the forward force. The forces to the left is equals to the forces to the right. So the component of this along the x-axis of tension, which happens to be T, and then T sine of theta. We already said when this is cosine theta, automatically the horizontal one here will be the T sine of theta. Now, so T sine of theta is equals to, that's the only force we have to the left, is equals to the equals to the friction force behind. It's balancing. So that implies also we can say T sine of theta. If you subtract the friction force, we're going to have a 0. So we have two equations. We have the first equation here and these equations there, and we can combine them so that we can get the tension force. And we can try now to reorganize the two equations to bring them together. And one way to do that is simply by first derivating the friction force in terms of the formula for the friction force. So when the system is moving, the friction force is usually given by the mu k, and then you multiply by n. And in this situation, we know mu k is given as mu, of course, and then n, this system again, n, we have it here. So we can reorganize this formula and say n is equals to mg subtract t cosine of theta. We can reorganize it like that. So with that, we know therefore we have mu k is there. So mg minus t cosine of theta. That's it. And with that one, now we can come back to our equation here and substitute in the friction force. So we're going to have t sine theta, that's one, minus the friction force is this one now, mu k, that is mg minus t cosine of theta is equals to 0. So open the brackets. So t sine of theta minus mu k mg minus times minus is positive, mu k t cos theta is equals to 0. So with that one now, so we can proceed on to bring the expressions with tension together, and then we can shift this to the other side. So then we're going to have t sine theta again plus mu k, and then you have t cos theta is equals to, that becomes positive, that is mu k mg. So factor out t, we get t sine of theta, and then plus mu k, then cos theta is equals to mu k mg, and therefore we divide each side by this expression so that we get t is equals to mu k mg divided by the sine theta plus mu k cosine of theta. So that's a solution to the first part of the question. So I think there's another part of that question which we can find now. Oh, this is a different question now. Have you tried this? And try this and see. So for this question, a block of mass 20 kg supported by a vertical massless cable is initially at rest. That's a very important statement. The block is then pulled upwards with a constant acceleration. Again, the word constant acceleration will enable us to use what we call the kinematics equations or equations of motion. So what is the tension in the cable? Again, we need to start by having a sketch. So we need a sketch of how this situation looks like. So I just have the block looking like this. So, and then we have some mass hanging downwards. I mean, the force downward here is mg, and the force upward here is tension, class. So we don't have normal reaction force. We don't have any other force here. Even though it's moving, air resistance, we're going to ignore that kind of a force. We just have a simplified system like this one. So it's moving up. So this system going to be moving up. By the way, we're going to also remove this part because it's moving. Let's remove the idea that it is stuck. I'm removing the idea that it is stuck because it's moving up with an acceleration which is equals to 2.32 meters per square second, like that. So the first part of this question, we can say what's the tension in the cable. So we just apply Newton's laws of motion. We know that because it's moving up, there's an acceleration. So Newton's second law of motion, which is F net, must be equals to mass times the acceleration, which is along the y-axis. So the F net here is, since it's moving up, the force upward is huge or bigger. So we're going to have as T. So T subtract mg, and this will give us the MAY. That's the whole idea. So we need tension. So T is equals to, take this to the other side. You're going to have M acceleration Y and then plus mg. So with that, the tension becomes the mass. So we know this can also be written as M factored out AY plus G. So mass for the block is 20 kilograms into bracket AY. So the acceleration is given here as AY, accelerating up, which is 2.32, and then plus 9.81. So with that, what's the answer? What did you get as the answer? 2.6 newtons. That's it. So the F net here, asking the other question is what is the net force acting on the mass? So the net force is simply, we take the upward force. So F net is simply the upward force tension and then minus the downward force mg. So the tension, we know it now, it's 242.6 minus the weight, which is 20, and then you multiply by 9.81. That will give us the net force. How much is the net force? 46.4 newtons. And the final part of the question says, what is the speed of the block after it has traveled 2.00 meters? So that one, you can simply write it as follows. Yes. So you can finish by saying, initially it was mu, that was the initial one, and then acceleration was given as 2.32. That's it. And then what else do we have? What's the speed of the block after it has traveled 2 meters? So y is 2 meters. And then finally, we're asking for the speed along the y-axis. Yes? How is? Y. So this is the distance because we are moving along the y-axis. If we are moving along the x-axis, I could use x. So since we are moving along the y-axis, just have it as y. This one, let's write it as v initial along the y-axis. Like that. So this will be the v final. So which is the best equation to use here? So v final squared is equals to v initial squared plus 2 A along the Y, changing that one, isn't it? Because we are given the acceleration here, we already have acceleration. It's not free fall. When we are dealing with the free fall, that's when we use the G. It's not free fall. So I'm done. Just this one, class, I'm finished. Okay. You get that? So with that one, we just now say the Vy is equals to the square root of. So what's the answer? 3.05 meters per second. That's it. All right.